Today we'll be deriving AX. Yeah, so we've got this cool function, y equals AX, or fx equals AX. We want to derive this bad boy. We know when we derive EX, that it equals EX again. Ooh. We know this, but we don't know that, so we want to derive this. Right in green, the actual deriving, this is just setup. So we're just trying to find what this is, the question mark. So it's going to be y equals AX. But to get this into something we know, like E, we have to change this to a problem that we actually know how to solve. So Jude and Margaret, you should know this. When you're using log laws, when you go like y equals 11 ax, what happens? What's the log law that you move with this one? Margot, solve it.
It goes up to a power.
What's the power of x equals a?
No, good try though. It's x natural log a now.
Oh yeah,
You've
no,
learned.
it's
just regular laws. You should have learned this
same
last
regular
year.
law.
Oh, sorry, I got the wrong way around. I saw the ln and for some reason thought to move it up. Yeah, no.
Not very smart, are you?
No, but I'm used to seeing it's just log. That the
You can make
ln
it
used
log
to be.
base e Margot so you can understand it. Is that better for you?
Yes, I
Can you
understand it now.
that? It's the same thing you've done before.
Yeah.
So if we know this, we can sub a for e. So we can do y equals natural log e of x because we know how to do this. We talked about it over there. So when solving this, Margot, what are we going to do this time?
You're going to put the x in front of natural log.
Well done, Margot. Finally, the learning experience. Better vote me for best teacher award. And we know what natural log e is because it's the same as log base e of e. What is it, Margaret?
1.
It's 1. Thank you, Sam.
Yeah, if you said me.
So the answer for this is just x. So we could say that we could do this backwards as well, could we not?
Yes.
Thank you, Margaret. So using the knowledge that we worked out over here, we can just do it backwards, couldn't we not? So we have an exponential to the power of a logarithmic function to say it's equal to k. We can solve this. Margot, how do we use the log law for this? It's okay. You can add some logs because you can't do log laws without logs. So I'm going to do natural log of e to the natural log of x equals the natural log of k. Is that okay with you, Margaret?
Yes.
Okay, that's good. Now we can use log laws to simplify this side because that's just the arbitrary side of the number. How would we do that? Yep, Sam?
Natural log x equals natural log x. You bring that out to the front of natural log e.
Yep, you got it, Sam. Natural log x times natural log e equals natural log k. And we know ln e is just 1. That's 1 times natural log x. Look,
Which would be x, sir.
natural log x is just natural log k. Now we're going to use this knowledge and jump all the way back over here. Is that okay with you, Margaret?
Yes.
So this is also equal to e to the power of natural log a power of x. We proved that that's that over there. Instead of x, it's ax. The ax from here is just x. Do you understand that, Margot?
Yep.
This is equal to that because that is that. Okay, so now we're just going to solve this. Y equals the e to the power of natural log a of x. Now, we can simplify the top part, can we, Margot?
Yes, we can.
How would I do it? E to the power of x to the natural log of a. Because the log laws, right, Margot?
Yeah.
Yeah. And now we just derive this as d over dx of the first function and the second function. Is that right, Margot?
Yeah.
Or more specifically, juniors have done this. So that's how we derive this. I'm just going to do this up here. So it's dx. And we derive the natural log A. A is just some random number. I'm just doing it there because I don't know it yet. That's the whole point. We're finding out whatever that is. A is just a constant. Does you understand that, Margot?
Yes.
So the natural log of A is just a constant as well.
Yes.
When you derive, let's just say if we had like 5x, if you derive that, we get rid of the x, and the constant remains.
Yeah.
So this would work in this scenario too. So when we derive the first part, it just goes from x, natural log A,
To A.
to natural log A. Do you understand that, Margot?
Yes.
Because that's just a random term. We haven't simplified it yet.
Epic.
Very epic. And then we derive the rest of it, which would be ax natural log A. See where we're going from here, Margaret? How can we simplify it from here? So now we have this term and this term in our derivative. We should know what this one is because this is just the ugly version of that. It's the same thing. We can move the x back out the front. I didn't mean to do that, but I did. It's the same thing. So this is just ax. It's natural log of a times a to the power of x. So that is your derivative of ax. Natural log a times ax. You got that, Margot?
I got everything now. Thank you,
Now,
Mr.
we're going to do a worked example.
Oh.
Let's just say derive 2x. How would we do that?
I don't know. You're the
We
teacher.
have the formula right over here, Margaret. This is the formula. Pump it in the formula.
It'd be
Bang on 7.
y.
2x. The 2 is the a.
That's
The natural log of a times 2x. That's the derivative. And that is how you derive a to the power of the x.
Yeah.
Now, Margot, I know you always hate math, and you're always asking, how is this practical in the real world? I got you. I got a real world application of this. You can use deriving an exponential to find the instantaneous rate of change of anything. Let's just say if I had a graph of like, I don't know, I'm a biologist and I'm measuring how fast bacteria grow. This is like time, this is bacteria in like thousands, it's like that. It's an exponential. I could derive this graph at any point on the graph to find how fast they're growing. So that is how you solve the derivative of dx and the practical application of it in real life. Thank you.
Yes.